Okay. Previously, I have shown how to use labkit to train the single slices of the images. Now I'm going to show another example that is not single slices but these stacks. For example, this is I have converted the raw CZF files to extract the debit channel, map2 channel, and teach channels. And I'm going to use the teach channel as an example to show how to train using these stacks instead of the single slices. We first take 3 representative images that we carefully selected, and open all of them in the image J. Okay, we can see that this is the stacks of the teach channel, and we are going to quantify the cell bodies. This is the first one, this is the second one, and this is the third one. Okay, first we need to combine them together. Okay, for the stack, the difference is that for the stack it is a 3-dimensional, it's not 2-dimensional. So there are more considerations when we want to merge them together into a single huge file for the training. So the best way is that the slices have the exact number of slices, so that these different images could be merged along the 10 points, so that this will not cause confusion between the different files. So you can see that this one has 29 images, this one has 27, this one has 21. So the slices are not does not equal. So we can either delete some slices to make them equal and merge along the 10 points, or we can just layer them as a huge stack. This is because the stack has so many slices, so we are no longer careful. We do not care too much about the slices in the top or bottom or near the boundary between the two samples. When we do the drawing, we just avoid the draw on these near boundary slices. Okay, so I will layer them as a single this stack, and I think this is also important because we cannot predict in the next similar experiment how many these slices we will acquire. If the next experiment we have 40, 45, or this will be not more compatible along T series, because we will do more work to make the slices number equal. It is not necessary. So it just makes them as a huge stacks. So we go to image stacks to concatenate, so that we have 3 images that opened here. And we can, if there are more than 4, we can select maximum 4. If there are more than 4 representatives, we just take all open windows and OK. Okay, so all the teach from we select stacks are merged into a single stack, and we save this. We save as a teach stack training from experiment 1. Okay, so we save as here, and now we can open in the labkit for training. Okay, because this is this tag, so we no longer see the scroll bar on the bottom, but we can see scroll bar in the right side. Currently it is invisible because it is a 3-dimensional view. We need to click this to the general 2-dimensional, and we can see the scroll bar. can see the two screw bar here, right? You can screw it up and down, and we click the settings. So important thing is normal is the smooth. If we click this, it will be more smooth, and this helps to draw the image. But this will also bring another problem I will talk about later. If you use linear mode, use smooth, linear smooth. Okay, first let's draw background, pencil draw background and foreground. We want to only get the cell bodies, so we draw foreground and cell body use eraser. And so the axons are also background, so we also draw the pencil background on the axons. Those are all axons. And this is a cell body, right? Even the inside is empty, we also need to label the inside empty as foreground and the cell body we want. And we change several slices in screw, and we draw this. This is a cell body. This is a cell body. I think this is a cell body. Oh, that's me. I think this is a cell body. Cell body. Train. So this labkit is good at the memory management, because it only shows results that we are looking at. So results show very fast. You do not need to worry about the rest of the part. It will not process unless we screw here, and it starts to predict here. We screw here, it starts to predict here. And we zoom in, it starts to process. Okay, we look at it here, it starts to process. So anywhere we look at it, it is lazy processing. It's called. Okay, where is the image? Cannot find it. Okay. Lazy processing. So here we see the results of the segmentation. Well, so many fibers are wrongly labeled as nucleus, so we need background correct. Because this kind of image is very hard to predict even for humans, so it is also hard for the labkit to predict correctly the cell bodies. So we need to do a lot of corrections and a lot of the training. The training work is very high, and we will get very huge classifier files. So it is hard. Okay, retraining. So this kind of image is almost at the boundary of the level that it can deal with. It almost cannot deal with such kind of image. It's unlike the static staining and the base tool with a clear boundary of so many fibers, and the fibers are strong and the cell bodies are so weak, so this caused a lot of problems. And we fill up these cell bodies and use eraser to clear this over. Sometimes you find eraser cannot erase this out. Sorry. This is a prediction results. You cannot erase the predict. You can only predict the eraser labeling. So So let's redraw. Is there something wrong? Okay, this is should be a background fiber. Sometimes it's very difficult to distinguish whether it is a background or it's just close to the cell body. For example, here it looks like a cell body. It also looks like an axon. Okay, should be cell body. Let's clean the background, make the background more clear. Okay, retry. Okay. Let's see how the results looks like. Okay, this axon should be background. Let's draw this background. Sometimes even people cannot tell whether it's a background or cell. So the computer also cannot tell. That's probability predict. It's background. Background. Oh, those fibers are background. 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 Okay, trim. This should be a cell body foreground. This should be a background. We return. So for this complicated images and huge Z stacks to train, it's better perform in the computer with. It's better to be performed in a computer with a GPU, because my laptop has no GPU, so every time is so tedious. Every step is so tedious. But here I'm going to show only a demo. So the real process will be much longer. The results. Okay, this should be a background. Okay, so for this, until try as many as time. Sometimes this need take several weeks to train. But if so whether it deserves or not, this depends on if you are continuing to do this kind of experiment and imaging for the every year, every 3 months or every month. If you are continually generating this kind of stringings and continually need to make such efforts, but if this is only one kind of experiment and there will be no save labeling. That because by the image notepad, you can see the number 76. As I have previously told you that this is the number how many slices this image have. So it is merged from 3 different stacks. So it is 77 slices there are. So if in the future for the secondary experiment, you also take some representative stacks and merge them as a stack, and use that stack to merge with the current experiment 1's training stack, and you will get a very large stack, and you save the stack and delete this TIFF. And for the labeling to reuse, you need to change this number 76 to the sum of the 76 with the next slices, so the total slices, and minus 1 because this is 0-based numbers. Save this and save, and then when you load the experiment 1, experiment 2, combine the representative TIFF to the labkit, the labeling will be automatically loaded. If you do not change it, it may also load, but the label does not correlate with the raw image. The position will shift to other slices because the shape does not consistent. For example, I will show you a bad example. And I close this. I will change this number to this is 76 and make it to 56. Okay, so number doesn't match. So what you will see? Let's try. Plug in labkit, open hand image with labkit. Okay, the labels should also be. Let me see whether the labels are loaded. Yes, it is loaded. You can see some slices, but it's completely at the wrong position. The cell is not the cell. It should be somewhere else. You cannot predict where it is. But if you correct this to the 76 and the 6, save them, and you reload to the labkit, you will see the labeling go back and in the correct position. You see, these are the